everyone, welcome to lecture 16 of this course. In the previous lecture, we discussed restricted lambda terms and type safe. In this lecture, we study the preliminary concepts required for understanding the principal type algorithm. So, today we are going to discuss term unification, substitution, most general unifier and the unification algorithm. So, let us first discuss the term unification. So, we are going to discuss this informally and later we are make a formal study on this term unification process. Unification is the process of finding a substitution for variables that make two terms syntactically identical. That means if T1 and T2 are two terms, so they involve different variables, say x, y, etc. and so on. So, the idea is that we have to make them identical, they will look alike. That is the meaning of syntactically identical, there will be no difference in this thing. So, for example, if we take a term lambda x dot x and you have lambda y dot y. So, we know by alpha renaming, if I do here lambda alpha renaming, I do lambda y dot y, and so now these are identical. Earlier they were not identical. So, this process of, so that means we have substituted alpha renaming and substituted, we have renamed alpha x to y, and as a result these two terms now look alike. So, this process of finding a substitution for variables that makes two terms syntactic identical is called unification, and when we are working with terms we call term unification. Now, a term can be a variable is a term. So, this is a variable is a term, first is a variable, it is a term. So, a constant is a term. Now, if T1, T2, Tn they are terms, then there you have a function symbol, this is also a term. So, we are defining terms in three ways. One is it is a variable, that means x is a term, variable x is a term, a constant is a term, and if you have terms T1, T2, Tn, f of that, f is a function symbol, that is also a term. And a substitution is a mapping from variables to terms. That means here what we did, x is a variable, we have replaced it with y. Now, y is a variable, now y is a term, variable is a term. So, this is legal in this sense, and so we obtained one such thing so that these two things look alike. So, unifier then is a substitution sigma such that sigma of m is equal to sigma of n. That means we have in that body of m we are applying sigma, which is a substitution. That means it will transform m, the structure will not change, but the variables and other things that will be renamed. After doing this both in m and n, they will look alike. That is what is called a unifier. If such a substitution exists, we say the terms are said to unify. So, we will take some examples. So, first is there are two variables, x and y are variables. So, you have these are terms T1 and T2, this is T1, this is T2. T1 is a variable, T2 is a variable. So, you want to make them look alike, that means we say x, you replace either, so this means x is replaced with y, or we say y is replaced with x. In either case they will look alike, so that is the unify. Now, here x is T1 is x, T2 is a constant, this is a constant symbol we write in uppercase. So, here we are replacing a term, substitution is a variable replaced by a term. So, this is the variable x and variable is replaced by term, term can be a variable or a constant or a function. So, here we replace this. So, now this becomes a. So, they look alike, they are identical. Here also it will be x, or it will be y, y. Now, functions with the same head, that means this is the head, they are same. So, we go on to see whether how to make them identical. Now, again there are two arguments in this function, there are 2. If that be the case, we will proceed. If it is not, say suppose there are 3 in the first one and 2 in the second one, then they cannot be unified. So here what we have done, x we replaced with b, so then this becomes b, and y replaced with a. It is a variable replaced with a constant, is a term, so now they look same. So this is the functions with same head. Now we have nested functions. That means inside a function the argument is also a function. So here first one is f, first argument is x, and second argument g. So this is t1, this is t2. Then all we have to do is we have to then combine x gz. This is one part we have to see whether they can be unified, and gy ga. This is the other, this is the second argument. This we are going to do. So here x we are replacing by gz. So it will be gz comma gz. So they are identical. So here we are replacing y with a. That means ga, ga. So they are identical. So we are done. So this is a substitution. You replace x with gz and y with a. Now you have terms like fx and gx. One argument, but here head is f and head is g. So that they are never they can never be made identical. So hence we say that there is no unifier for these two terms fx and gx. Next we have a term x. This is t1 and this is t2. Now here interestingly x occurs in t2 as well. X occurs in t2. That means if we say x is replaced with fx, so the first term will become fx, second term will become f of x. And if you go on doing, it will be this infinite many and this. So they are not unifiable. And this is called the occurs check problem. That means a variable in t1 occurs in the term t2. If that be the case, they are not unifiable. So now let us formalize this idea of type substitution, and we are going to use the definitions and lemma from chapter 3 of Hindley's Basic Simple Type Theory book. So definition of type substitution is, a type substitution is any expression written in this way where sigma i's are types and the ai's are distinct type variables. So a1 to an, these are all type variables and these are types. So a1 to be read as a1 is replaced with sigma 1, a2 is replaced with sigma 1 and so on, an is replaced with sigma n. This is the notation that we have just seen informally. That means for any type tau, we define S tau to be the type obtained by simultaneously substituting sigma 1 for a1, sigma 2 for a2 and sigma n for n throughout tau. We call sigma S of tau a substitution instance of tau or simply an instance of tau. That means from tau, by making some substitutions, we have got another say type. So we get tau prime say, that is called a substitution instance or an instance of simply say tau to tau prime. Tau prime is an instance of tau. So this set of type variables a1 n we call the domain of S. So when we say this is a substitution S, then we have a domain of S. And these variables sigma 1, sigma 2, vars sigma 1, sigma n will be called the range of S. So substitution then is a mapping from this domain to this range. You are taking a type variable and you are mapping it to an element inverse of sigma 1 to sigma n. Now, let sigma and tau be two types. We say that these two types are unifiable if there exists a substitution S such that the substitution of S onto sigma is the same as the substitution of S onto tau, and in this case S is called the unifier. So, consider the following examples where you have sigma is AROB and tau is DROB. So, that means already B part it is matched. So, either we make D to A or A to D. So, you have either A is replaced with D or D, both are type variables. So, A is replaced by D or D is replaced. So, they will look alike. So, the unifier S is A replaced by D or D replaced with A. Now, second example, we have A arrow B and now we have D arrow B arrow E. Now, suppose we unify A and D. So, we replace A with D. If you replace A with D, then these parts will be same. Now, we have to unify this part, that means B and B arrow E. Now, B and B arrow E, they cannot be unified. These are different. These type variable, these are arrow type. So, B and B arrow E, they are not unifiable. Hence, this pair of sigma and tau, they are not unifiable. Now, the third example, we have C arrow E and we have B arrow C. So, we can make C to B. So, then these parts will be same. Then now these parts will become, once we make C to B, C is replaced with B and we apply it here, that means this will become B arrow E, this will become B arrow B. That means now we can E will have to be same. So, we make E to B. So, that is it what we have. C is replaced with B, E is replaced with everything. So, then final answer will be B arrow B. So, the final answer C will be, C, this part becomes B arrow B, this part will become B arrow B. They are alike and hence the unifier is this S. Now, we consider composition of two substitutions. If S and T are any substitutions, say S is involving type variables A1 to AN and T involves the type variables B1 to BP. So, we write S composition T as these things, maybe it will be difficult to read here. So, it is not, we read like this. So, we take the parts that are there in T. In this T expression, what you have, you apply the substitution S onto these things, T1, T2, tau P. So, you get this part. So, there will be P such things, P variables are there, that means all the tau 1, tau 2, tau P, we have replaced it with S of tau 1, S of tau 2 and S of tau P. Now, the other part, it is not that here we keep it like this. Here what we are going to do, it is this, that if you take the domain of S is A1 to AN and domain of T is B1 to Bn, we take the difference of these two, that means we are doing the set difference of this set A1 to N, that is the domain of S and the domain of T set difference. That means the elements in S not in type variables in S not in T. This is what we are representing here. That means this is sigma, we are writing I1, A1 dot dot, and these are the elements are coming from this. This is the idea about composition of two substitutions. So, let us see this example will make it clear. So, we have T is this and S is A, E replaced with A. So, here the domain of S is E and the domain of T is B and C. So, S domain of S minus domain of T will be E, elements in this and element not in this. So then this part, there are two parts. This is the first part, that is domain of S minus domain of T. So this will be only this part, and the T part will be same. T part, what number of variables that are there? T has two variables, so there will be C and B as it is, and in the tau part we are going to make the substitution. So you are going to write S of E and S of E. S of E is A, S of E is given as A, so it will be A of SE and A of B. This is already there, it is already S is A arrow E, A slash E, so we have this. So then S composition T is E replaced with A replaced with E replaced with A, C replaced with A, and B replaced with A. So then we can have this lemma which says that domain of S, substitution of S and T is a union of the domain of S and the domain of T. And then if I apply the substitution S dot T onto tau, it is applying tau onto tau first, applying T onto tau first, then the result we are going to apply S. And this dot substitution operator is associative in the sense that R dot S of T is the same as R dot S of T. So the idea then is, so this one what we said, that means if I want to do composition by rule 2, I can do it in this way. I will first apply tau, onto tau I will apply T, that is the second part, second argument of this one. Then the result, onto the result I can do that S. So this is sequentially I can do onto something like tau. Instead I can directly do S of T. S and T they are given, so I will do it and then apply it on tau. That is the idea. Whichever you prefer we can do. And next we have this definition. This we are going to use when we are going to study principal type algorithm. The deductions we are going to make substitutions. So if I have S of this tuple tau n, that means we are applying S individually onto this. So we are going to get S of tau 1 dot dot S of tau n. And if gamma is of this form, x1 gamma is like this, is x1 sigma 1 xm tau m. This is the context, the type assignment. Then when we are doing S of this, it means here these types are going to be substituted. This will be, this is actually, this should be, either we write sigma or we write tau. So we write sigma here. So here it should be sigma. So it is a, so it should be either we write consistently tau 1 or we write sigma. So here if I have this assignment, then S of tau, S of gamma means this sigma 1 sigma m, this will be replaced by S of sigma 1, S of sigma 2 and S of sigma m. This is what it is saying. Now when we have this gamma, this is the formula gamma, in that context m has type tau. This one substitution of S we are doing, that means we are doing S of gamma, that S of gamma we know it will be like this. Here we have to apply S and m colon S of tau. This is what we are going to use in TL lambda in PT algorithm. Okay, now we are going to discuss most general unifier, also written in m.g.u. Informally, most general unifier means a unifier that has the least constraints, that is general. So formally we define m.g.u as, so m.g.u of a pair sigma tau is a unifier u, which is a substitution, such that for every other unifier S of rho tau, we have S of rho the same as S prime u of rho for some S prime. And from the previous lemma we have seen, that means this part is basically composition of S prime u. That means S can be written as S prime u. The idea then of general unifier, if u is a unifier of this pair rho tau, then for every other unifier S, this S can be written as a composition. S can be written as a composition of S prime u for some S prime. This is the meaning of most general unifier. That means if V is the same as u of rho for m.g.u u of rho tau, we call V a most general unification of rho. Now, suppose we are given u and we have to show that indeed it is m.g.u. So, the idea here would be, say rho is C arrow E. With an example we are going to illustrate, and tau is B arrow C. Let S is this part. That means we have here, what are the type variables here? C, E and B. So, C, E and B we have given substitution. This is S. Let U be the m.g.u, where it is involved in two variables C and B. And let us say S prime is A and E replaced with A. So, we have to verify that S is the same as the composition of S prime u. So, S prime is u is what? S prime u by the composition rule will be S prime, this part is S prime is AE, and we will apply S prime onto u. That means S prime E, this part. S prime E is S prime E, S prime E is A. So, this is A, this is A. And now we get A, E, A slash E, A slash C, A slash B. So, which means this is that, this we have obtained this. Thus, U is m.g.u. So, as we can see that this is having involving 2. This substitution involves 2. This substitution involves 3. This is also a substitution. This is also a substitution. But this is most general. That means least constraints. This is the idea about m.g.u. Now, the unification problem is, we have to define the unification problem. Now, before that, we can see that if there exists a unifier of rho tau, then there is also an m.g.u for rho tau. If there is a unifier for rho tau, then there is also a most general unifier for rho tau. Now, the problem is, given a pair of types rho tau, is there a unifier for rho tau? That means, can we come up with an algorithm that will take this pair as input, say yes or no? Yes means it is typeable and it will say there is an m.g.u, or it will say no. No means it is a correct statement that indeed there is no unifier for this pair. And we have an algorithm that is called Robinson's unification algorithm that gives an answer yes along with the m.g.u or no otherwise. So, now give the algorithm. The outline of the algorithms is like this. It is given by Robinson in 1965. So, the outline of the algorithm is given below. So, first step says that we maintain a set of equations. These are the constraints, and we repeatedly simplify by the following rules. So, 2.1 says if we ever arrive at a pair XX, that means they are identical, we remove it. If we have a pair XT with a variable X not occurring in T, then we replace X with T, that means substitute X, that is assignment, X is assigned T everywhere, and that is called occurs check. We call occurs check to be successful here at 2.2. If both sides are functions with the same symbol, that means you have f of something as T1 and f of some other thing as T2, then now we know the heads are same, so we unify their arguments. That is 2.3 says this one. And if their top symbols are different, that means you have f of something and then g of something, obviously they cannot be unified. So we say failure, return failure. And 2.5 says the occurs check fails. That means x is there in T So you have an example like x is equal to fx, so it will be failure. So the occurs check problem means a variable is unified with a term that contains the same variable. Here x and this term fx, it contains the same variable. That is called the occurs check problem. So then this algorithm, if we apply, either we are going to get a unifier which is m.g.u, or it will say no, there is no unifier. That occurs check will fail. So we will illustrate with some examples. So the first example is, we have a term involving a head f, and there are two arguments in this first one, and there are two arguments in the second. So by that rule, initial equation set will be, this will be like this. These two terms we are going to place in the equation set. Then step 1, since their heads are same, so we will break into their arguments. So and there it will be x, we are going to see whether this pair x and gz and gy and ga, this pair wise we are going to now try to match. So x gz equation set now becomes x gz, this pair, and gy ga. So consider the first equation. We have to see the occurs check, success or not. X is a variable, x does not occur here, so occurs check is success. So we can do the substitution like x, replace x with gz, so you get sigma. Apply everywhere. If we do this, it will be same, so then we can remove this part. Next, we have to consider second equation. Now in our equation set, we have only this thing. Now again the heads are same, so we now look at their arguments. So we have y and a, we have to do. Again we have to say occurs check, it is success, y does not appear in this T2, so we replace y with a. So now it will be same, so then we have removed, so we have the empty set. So our substitution then is x is replaced with gz and a is replaced with y. So this is the substitution, now the set is empty, so we stop here. So this is the m.g.u. So sigma that is called is the m.g.u. Now the next example. So again we have term gx and another is g of fy. So their head initial equation will be like this. Because their heads are same, so we break up into x and fy. Now we have to check the occurs check success. X is a variable and x is not there in fy. So we can substitute x with fy. So we have occurs check success. Apply sigma everywhere and remove the terms of the form xx. So we have got them. So now we have removed it. Now our equation set is empty, so we are going to stop. So we find the substitution is x is to be replaced with fy. So if we replace it as fy, we will get g of fy, here also g of fy. This is the m.g.u. So to note that x s prime is another substitution. That is, if we replaced x with fa and y is a, so it will be g of f of a and it will be g of f of a. It is a unifier, but it is not a general one. So this is a general one. So this one we can obtain as an instance of this s prime we can get. S prime is an instance of this s. General in the sense we have least constraints, it involves only one variable. Here you have involved in two variables. You are saying x is something, y is something. More constraints you are imposing. Here least constraints we have imposed. And then s prime is an instance of this. If that be the case, s is a m.g.u. Now the third one example, we have x and fx. And now initial equation set will be x and fx. Now x is a variable and x belongs to fx, so occurs check fails. So here it is not success, it failed, no unifier exists. And this is the situation of occurs check. So there is no unifier for this x and fx. We have discussed the following in the today's lecture. So we have discussed term unification, substitution, most general unifier, and the unification algorithm. So please see to chapter 3 of this book by Hindley. Thank you for your kind attention.